Hello. So this is MATH321, and I'm going to review the fixed point theorems that you've seen in class and in the tutorials, and I'm going to talk about errors. Right. So there's a couple of components for the proofs of the fixed point theorems that are very important, and I'm going to talk about those right after I refill my ink. Right, so there's a couple of core concepts. One of those is compact sets. One of those is Cauchy sequences. What's the definition of a compact set? I'm not going to give you the full definition because we don't need it here. We're only going to be working inside the real numbers, so we don't need to know about anything else. So in this case, we can say that a subset C of R is compact if it is closed and bounded. Closed meaning that the complement of the set is open, and that means that for all x inside the complement there exists a radius, so that x minus r, x plus r is a subset of the radius. Think closed intervals. Bounded means that for all x inside C, there exists some number big enough so that for all x inside C, the absolute value of x is less than m, and that's basically equivalent to saying that C is a subset of x minus m, x plus m for any x inside C. Closed and bounded implies compact. Compact meaning kind of like it's small, that the set is somehow a condensed thing, just like a closed interval. So closed intervals are compact sets. We need to know what a Cauchy sequence is. So sequence is Cauchy if and only if for all epsilon greater than 0 there exists some number inside the real numbers, so that m and n bigger than this number implies that xm minus xn is less than epsilon. That basically says that the distance between the points as the sequence goes on is becoming smaller and smaller and smaller. Okay. So these results links together in nice ways, and it's those linking together of those two concepts of a compact set and the Cauchy sequence that are important. I'm not going to prove these results, but you should read them, or you should go learn more about them if if you're interested in knowing more. Go read about them. They're very common. Okay, lemma. If a sequence is a subset of C, a compact set, then there exists little c inside C and a subsequence so that the subsequence converges to the element of C. If a Cauchy sequence has a convergent subsequence, then the Cauchy sequence itself converges. And related to this is accumulation points of Cauchy sequences are unique. Okay, so now we can talk about this theorem, one of the theorems we've seen in class. I'm going to try and fit, I'll start on a new page. So you've seen two main theorems in class. One of them assumes the existence of a root and one of them does not. Let G be a function and suppose that there exists a number lambda less than 1 and rho greater than 0 and x0 in R, so that 1 x0 and the first iterate of the fixed point method are close. And that for all things close to the first iterate, we have that the function satisfies the Lipschitz condition. Then all the iterates defined by this equation are inside the interval. There exists alpha inside the interval, so that the iterates converge to alpha and the distance between the iterates and alpha satisfies this condition. And because lambda is less than 1, this tells us how fast this is going to 0, and of course this is the error, so it tells us how fast the errors are going to 0. That's the convergence rate. And 3, alpha is unique. So here's the other result, let G be a function with a fixed point alpha. Suppose there exists rho greater than 0 and lambda as before, so that for all x0 inside alpha minus rho plus alpha to alpha plus rho, we have that the iterate compared to the fixed point has a certain bound on how far away it's allowed to get. Then 1 for all I, where we define the iterates like this, xi is the image, xi plus 1 is the image of xi under G. We know that the xi's are inside the interval about alpha this time rather than the interval about rho 1. 2, we know that the xi's converge to alpha, and the statement of the theorem you've seen doesn't include the convergence rate, but you can pop out the convergence rate for it. And 3, alpha is unique. What's the main difference? The main difference is that if we don't know the root, we need a bound on how far away the first iterate is from the second iterate. If we do know the root, we don't need that bound. So this means this might apply to more points, a larger interval than this theorem. But for this theorem, you don't need to know that there's a root. You just need to check that this is true, and this is true. And you can test that by stepping along the real line, for example, picking points from the plane or whatever situation you're in. I'm going to do the proof for this one, but I've done the proof in detail already, so I'm just going to sketch it. First, show that xi plus 1 minus xi is less than or equal to 1 minus lambda I rho. Do that by telescoping. Okay, and then you can use this to show that xi plus 1 minus xi is less than, well, you do this by telescoping on this condition, and you do this step by telescoping in the traditional sense of adding 0 in. 1 minus lambda, oops, and that proves 1. 2. Closed and bounded things are compact. Is compact, and 1 implies that the sequence of iterates is Cauchy. Implies there exists. Well, it turns out that we get 3 as well. Oops, inside the interval. So the xi's converge to alpha, and we already know the bound on the convergence because we proved that earlier on. 3. Alpha is unique as this sequence is Cauchy. Now I actually proved all of this in detail, except that compactness implies the existence of the root. That you should have a look at and think about yourself. You might be able to get there, and if you do, well done. The conditions of that proof are so important that I've reiterated it again and again and again. We've gone over it many times in class. It underlies other fixed point techniques, which are important to know. Right. So I've shown you this result several times already as well. If an element of C1, I'm just going to rewrite it using the notation of the previous result. And this basically says that if the derivative, the absolute value of the derivative is less than 1 everywhere, then you can find an appropriate lambda. And this follows from the mean value theorem very easily, like I have done and shown you in class many, many times. Proof mean value theorem. Go ahead, prove it. Actually go prove it. Okay, so all of that shows that our fixed point methods should converge. I mean, the algorithms say that the convergence must occur, right? So when we write these functions into the computer, and every time we evaluate these functions in the computer, numerical errors will be involved. And these algorithms haven't taken any account of numerical errors. They've only cared about the error of the convergence, the error associated with our approximation of the function. How close are our iterates getting to the root? But they don't care about the behavior of the algorithm with respect to numerical error. So this next result shows you what can we bound how close the iterates get to the root when we have numerical error? And the answer is, of course, yes, but we don't get preciseness anymore, not necessarily. This is a generic feature. You've seen this before with the other fixed point methods you've seen. So first up, I'm going to assume certain things. So delta from the real lines into the real line be such that delta x is the error, numerical error, that results from evaluation of g at x. Okay, so what this means is that in the computer, maybe you could say this, the floating, no. In the computer, evaluating g at x gives gx plus delta x. Now I'm going to make an assumption. Assume that there exists delta greater than 0, so that for all I, so that for all I, delta xi of our iterates is less than delta. So I'm assuming that the total error for evaluation at an individual point for the iterates is bounded. Not as ridiculous as it seems. Our iterates are going to be converging to some point, and presumably the errors in the evaluation of the function g should be related in some way to the errors when you evaluate at that root. If the function is continuous, I guess. And you don't have massive changes in scale, I suppose. But anyway, assume that the errors are bounded. This is the result for errors. Let g, x have a fixed point alpha. And assume that our first iterate is close to the root for some row, and that for all x inside, we know that g of x minus g alpha, this is the normal Lipschitz condition, for some lambda greater than or equal to 0, less than 1. Okay. So our x0 has to be row close to alpha and has to be row 0 close to alpha with related to this. You know what? I think I've written this all down wrong. Let's start again. Theorem. Let G have a fixed point alpha. Suppose there exists row greater than 0, and a lambda, so that for all x within row of alpha, we know that g of x minus g of alpha is less than or equal to lambda x minus alpha. That's better. And assume that there exists row 0, so that row 0 strictly greater than 0, less than or equal to rho minus delta over 1 minus lambda, so that x0, the first point in our iterate, the first point in our sequence, is within row 0 of alpha. This is an allowance for the error. Then, if xi is equal to g xi minus 1 plus delta xi minus 1, the error in the evaluation, then these things all lie in, so we don't escape our interval. It's great. That's bounding. And alpha minus xi, the error is bounded by this quantity. This is guaranteed to be positive by this condition over here, which I think I forgot to take note of in class, but I think there was somebody trying to tell me that, so thanks. Note, this does not depend on the iterates. That is a constant amount that does not go away. If the rate of convergence is very good, that means that lambda is very small. That means this is very close to 1, which means that the difference between these will be close to the upper bound of the error. If the rate of convergence is very bad, so lambda is very small, the denominator will be very small, and this bound could be very large, and your iterates, your approximation of the iterates based upon the error could be very, very bad. At least the theorem tells you that, rather than trying to figure it out as you go, and because debugging numerical code is difficult. Proof. Right. First note that x0, an element of alpha minus rho 0, alpha minus rho, alpha plus rho 0, implies that alpha minus is less than rho 0, which is less than or equal to rho minus delta over 1 minus lambda, and that's certainly less than rho. Now, alpha minus xi less than or equal to g alpha minus g minus 1 minus delta xi minus 1, and this will be less than or equal to g alpha minus g xi minus 1 plus delta, and that is going to be less than or equal to lambda alpha minus xi minus 1 plus g. And if you chase that series of steps all the way through, what you end up with is and this is this bit here we know is less than rho. Well, we know it's less than rho 0, so let's do that. Plus everything else. we can, the sum is a geometric series, so we can write that down. That's lambda I rho 0 plus 1 minus lambda I over 1 minus lambda delta. And if you rearrange that, you get delta over 1 minus lambda plus lambda I rho 0 minus lambda. Well, we don't have to have a rho 0 in there because this can also be a row. So we can put rho in there if we want to, which is great. And this thing here, certainly less than or equal to rho 0, because that's less than 1. This is less than 1, rho 0 plus delta of 1 minus lambda, which is certainly less than rho. Less than rho, and less than rho gives us that all our iterates are inside the appropriate bound, which I guess I had written incorrectly. And this gives us the form that we wanted at the end. Stopping conditions. It's suggested by Atkinson that this algorithm should stop, or the iterates should stop when is approximately equal to. So this is roughly saying if delta is very small, then this is very small. We've got a rho 0 in here. So we basically want when this term and that term are equal. You're going to have this dominating, and if delta is 0 and lambda is good, then this will be small anyway. So you might as well be very close. At least that's the heuristic hand-wavy argument. But at least if you have this as a stopping condition, then you can calculate how many iterations you want to do. So if you assume that this is actually an equals sign and rearrange everything, what you get is lambda k equals delta over 1 minus lambda rho, and that implies that k is equal to ln 1 minus lambda rho divided by delta over lambda 1 ln over 1 minus lambda. Lambda is less than 1, this is positive. Lambda is less than 1, delta is going to be very small, this is positive as well. So if your convergence rate is very good, lambda will be small. If lambda is small, the denominator is very big, which means this whole thing will be very small, as we should expect. If your convergence rate is very bad, lambda will be close to 1, this will be close to 0, this whole thing will be very big. Okay, orders of convergence and Taylor's theorem. Page 7. Taylor's theorem basically says that if we're expanding out our fixed point method around the root, that this is so that's Taylor's theorem with remainder, when G has to be suitably differentiable. So roughly, this is we can say this is going to be some iterate. So we can say we've got error gx minus, that's going to be alpha, that's going to be some iterate x, is going to be, let's say, I plus 1. If this is xi, then this is xi minus 1, that's alpha, so that's the error when you subtract them off, is equal to g dash alpha times the previous area, that would be xi. So if the first derivative of our fixed point method is non-zero at the root, then we have a linear approximation. Of course, if the first derivative is 0 at the root, then we would have second order approximation. I'm kind of ignoring extra terms and things, but there you go. So in particular, if 0 is equal to the first derivative, and the second derivative is also equal to 0, all the way up to the nth minus 1th derivative is equal to 0, assuming that the function is suitably differentiable, then the same argument above with Taylor's remainder implies that G is nth order, which is interesting. Okay, examples of fixed point methods. Gx equals x minus m fx, chord method. Fixing the slope. This is geometrically picking a point and ensuring that you always use the same, oh well, you have a cycle. Ensuring that you always use the same slope. G dash x equals 1 minus m f dash x. That implies that is equivalent. So this implies that this statement, the derivative is less than 1, which we need for the convergence results, is equivalent to saying that m times f dash of x is less than 2. So you need to know the interval that your iterates are all going to lie in, which you can get from the theorems, and then you just need to choose your m so that this condition is true, and hey presto, chord method works. Of course we can do better than that. Newton's method. Newton-Raphson. If you work through the calculation and you do the quotient rule and you have some counselling involved, this is so that at the fixed point, remember, and this will be the root, and that immediately implies that Newton's method is second order. Great. Easier. Now it is also possible to use this Taylor expansion method to write down a general method for, wow, general is probably a little strong, but at least write down a method for finding fixed point schemes of arbitrary order. So I'm going to show a third order fixed point scheme. Using Taylor's method. So here's my function I'm trying to find the root of. Taylor's theorem with remainder. Let's assume that our iterates are very close, so I can ignore this bit. So that if I ignore the second order portion, then what I get is that f of x equals 0 is equal to f of x plus the derivative at f of x times xi minus alpha. Okay, so now I'm going to write h is equal to xi minus alpha. So in other words, if xi plus h should be equal to alpha, except that I've dropped off all the second order terms, so that's not quite what I should write as xi plus h. Is kind of like alpha. In particular, I can write xi plus 1, which will be my next approximate for where alpha is going to be equal to xi plus h. So all I need to do is solve for h. And what's h? Well, h is xi minus alpha, there's xi minus alpha, so I have 0 is equal to f xi plus f dash xi h, and that implies that h is equal to minus fxi over f dash xi, and then I have my numerical scheme. Wonderful. So if you take Taylor's theorem out to higher orders, you can do the same thing. Of course, each time you take a step out to a higher order, what you get is, instead of a linear polynomial in h, you get a quadratic, and then a cubic, and then a quartic, and so on. And solving for h under those circumstances can be rather awkward and difficult, and so people have devised a bunch of different methods to try and handle that. But at least in one case you can do it directly. Haley's method. Xi plus 1 equals xi minus fxi over f dash xi. Great. Times 1 minus fxi over f dash xi, f double dash xi divided by 2 lots of f dash xi inverse. That's third order. And if you're very clever, you can write down a dth order method. Which is called the householder. And they're all related to insights to do with the Taylor's theorem expansion and the idea that you can kind of ignore stuff and hopefully those remainder terms get very small. Right, that is fixed point methods. And so after this, we are going to have a look at multivariate fixed point methods very briefly, because everything's basically exactly the same. Just the notation is different, and there are some different ideas involved that it's important for you to see. And then linear interpolation.